Good evening, everyone. Let's not be blindsided. All products have security vulnerabilities. The question is in the community, how long should a vendor take to release a security fix for a vulnerability in their products? The zero-day emergency response team says 0 days. I have Gil Dabach here, and in his talk, VML, any third-party vulnerability, third-party patches, he will describe how they reverse engineered security vulnerabilities and provided third-party patches to products. Please welcome him.
Test. Do you hear me well? Yeah, test, all right. So, my name is Gil Dabach, and I came here to lecture about ZERT and a few things about me. So, after I wrote the patch for the VML, the first time they told, this is a quote from eWeek, the Israeli programmer and reverse engineering enthusiast Gil Dabach. That is, so that was on the 22nd, and 3 days later, the Israeli reverse engineering specialist, Gil Dabach, and you get it, like 3 days and I became a specialist in reversing, so. Anyways, actually, I consider myself a computer hacker. That it doesn't mean I hack into other people's computers. It means I really love computers, and I get excited about a few lines in C or some assembly algorithms, so things like that. Maybe some of you know the distrom disassembler. It's an open source disassembler that a very successful one is used widely, and I'm the guy who wrote it. And this is all hobbies and stuff I do in my free time. Actually, I work in DigiCash as a regular programmer. Okay, so after all, we are here for ZERT, and that's actually zero-day emergency response team. And let's see. So actually, there is a reason that we founded this team, and it's about 0 day. And 0 days actually is a security hole in applications. And I'm not a dictionary or anything like that, but I want to define the meaning of 0 days. So as long as there is a security hole in any application and people exploit it, or hackers, then it's called a 0 day, as long as the vendor doesn't do anything about it, and maybe if it does, and if it doesn't, it's not patched. It doesn't matter. So the foundation, actually after Ilfak Guilfanov WMF patching that he did on his own, we thought about, or actually Gadi Evroni is the operation manager of ZERT, and he thought about, let's do this cool thing, patch 0 days out there because the vendors are too slow and maybe it will help other people. So he called me and said, let's do something. So the goal, if I was Miss America, I would say it's to save the world and make it better. But, but I'm not, but yeah, actually this is kind of a goal. So it's all about incident response. After all, this team is emergency response team. So it means if there is something that actually in ZERT, we call it ZERT-worthy or something like that. So if it's a ZERT-worthy, it means the team should work on a patch and release it as soon as possible to help the community. So for example, it was the WMF exploitation, or if you remember, there were like Red Nimda or Sasser, or there is another one. Come on, another worm, popular one. Blaster, yeah. Okay, so the point is, we want to patch important 0 days, because if you, like a worm, you don't have to do anything and you get owned. So this is important. But if someone sends you an email and ask you to open the file, then we can't do anything about it. So in this talk, I'm going to talk about patching in general, and you will soon understand what it is all about, the challenges, the problems we have, and how to solve them. And in the VML vulnerability, I'm going to speak about how I did it, the researching steps I took, and the help from the team. And later on, the latest 0-day is the animated cursor. And one other thing, I think this, I'm not sure whether it's the first presentation about patching, because all the talks in DEF CON, Black Hat, and Recon, or whatever, all these congressions are all about attacking. So this time, someone is really going to talk about practical patching. So what is patching? Actually, in the simplest form, it's just changing some data in an existing software. The data can be code or data. Sorry, again. The data can be either code or real data, like strings or structures and stuff like that in the data section. So usually when you patch something, you want to change the behavior of the application you patch. It can be, for example, sometimes you want to enhance the software, like if there was a bug or something like that, then you want to fix it. And okay, just a moment. And another type of patching is cracking games, although it is illegal, of course, or software. And back to the latest bullet, patching can be done on disk, which means you can override the file or you can do it in memory, and we will get to this later. And like Ilfag Guilfanov said, that's the man behind the IDA Pro, he said that uncracking software, it's a new cool word that we use in ZERT, so we uncrack patches. Oh, sorry, we uncrack 0 days. Okay. So the problems we have with patching, it's actually some complexities and challenges we have to bypass and to solve. So actually there are lots of different versions of, for example, the DLL of the VML. Okay, there are a lot of different versions of the DLL of, for example, VML. It's named VGX, and it's really hard because the code changes between the versions and the code moves around because every time the compiler changes stuff and they compile a new version and they add code or remove code, it always goes up or down, and there is no room for the extra code that you want to add, the code that actually fix the vulnerability. And there's another problem that MS hot patching, which is a good thing, we can't use it anytime we want because it's not there always. If you have an old version of Windows, it doesn't exist there. And there is another problem, which is the Windows file protection. You can't overwrite important files like DLLs or system files, things like that. So we have a few alternatives here that I sat down and thought and used some help with the guys from my team. And we have to remember that we don't want to change the file as much as possible because every change can lead to another bug or failure of the application. So the first alternative we have is patching the executable itself by adding a new section or by finding some room in an existing section and put our code there. So there are a few problems with this alternative because it's really hard to do such a thing in the short time you have. It's not like I can sit down and develop it weeks before I know there is a 0 day coming out. And it's a big change for the executable file and time consuming. I said it's really hard to program such a thing, but in a long and in a short time. And per version patching, it's very popular. If you see EI patch or iDefense and companies like that, you have or actually they have all the DLL's files, and they check each one of them, and they do a spatial patch per version. So the problem here is that if you don't have all the versions of the DLL in advance, you're screwed. So another patching alternative is the hot patch. We said already that we have 7 bytes. Maybe some of you recognize the CCs and move EDI, EDI. So the problem with this approach is that it's not good for static or in-disk patching, and the other problem is that you have to patch all the callers and not the vulnerable function, because probably it's str copy or mem copy and things like that that can't be patched easily. So you have to patch a few of the callers, and then you need more signatures, and it becomes harder. So there is spot patching, or I don't know what's the professional word for term for this, but this is what I came up with. And it's simple. It means that you search for something that you know in advance how it looks like, and all you do is replace it with a different code that probably should be with our fix, the ZERT fix. The only problem with this approach is that it doesn't always have the same signature matched for all the versions you want, or either way, it's generic. If you have a good signature, you will find all the places you need to patch. Okay, so now I'm going to talk about the VML patching, and I will show some steps that I did in order to find the vulnerable code and how to fix it. So a bit of a background about VML. VML is vector markup language. It lets you describe how to draw graphic stuff on the on the screen. And it was proposed by MS in 1998. The problem was that it was rejected, but Microsoft still insisted to use it, and that's the outcome indirectly that we have this 0-day or add. Anyways, this is some of the things you can draw with the VML, and you have 3D stuff even, and grow shading and crazy things. It's really nice. But one day, in September 2006, someone found, Adam Thomas, a researcher from Sunbelt, found this 0-day. Okay, so the exploitation actually downloads a Trojan and runs some code, show pop-ups and adwares and things we don't like, and this is the good case. The worst case is like stealing your login credentials for your bank and stealing your money, stuff like that. Okay, so now I'm going to talk about the vulnerability itself. So actually, it's just a stack-based buffer overflow, and there is a fill method that's the fill of, if you have a rectangle and you want to fill it with some color, then there is a buffer overflow, and the affected file is VGX DLL. Now, if we use the PDB files from Microsoft, we know the exact function, and soon enough I will show you how I did it. But the vulnerable systems are Internet Explorer, and I mark it specially with asterisk because it's not true. We will later get to this point again. And even the XPSP2 is also vulnerable to this 0-day. So actually just surf and get pwned, and you're screwed. So I ask myself, what if DEP is enabled? DEP is data execution protection, and it's a way to prevent from buffer overflows to get executed and to get pwned actually, but technically way. So there is hardware enforced DEP and software enforced. It doesn't really matter. DEP can be bypassed with read to lib and things like that, but actually it will mitigate most of the attacks if the DEP was default on for Internet Explorer. The problem is that it's not. So the HTML exploitation of the VML is pretty straightforward. We can see here the fill method with the long buffer, which will eventually buffer overflow the stack buffer, and you get some code. There is this behavior line you see here with behavior URL default VML. This is the line that actually loads the VGX DLL that has this fill method function called with the argument. And so this is another thing I came up with and call it vulnerability point. It's actually the instruction or the function itself that has the vulnerability, or that overwrites the stack in this case. So what I did is taking the old code of the HTML exploitation, put a big buffer there, and this is what happens immediately. And notice that this DLL is not verified for some reason, I don't know. So now we know this DLL is the VGX DLL, and we can continue from there. And this is what we do. And what happens next is that we raise an access violation because there is a pointer on the local stack that tries to write somewhere not in memory. So we get an access violation. So now that we have this access violation, we can see the faulting address of the instruction and start analyze from this point. So the parser tokenizer, probably, nobody really knows the official name of this function, is ptoke. That's what I showed earlier with the PDB symbol. And this ptoke actually is a C++ function. And the reason I say so is because there is this move edx, ECX plus VML null terminated string input. So this is where it gets the string from the HTML code and puts it in the edx register. And later on, we can see that edx is the index that counts over the string, and it takes words. This means it's Unicode or UTF-16, and it copies it to the buffer in the member of the class of the instance, of course, because again, ECX is used, it means in Visual C at least that it is a C++ code. So what we have next is this line, move edi dx. Dx was already copied here with the input you supplied, and now it overrides the stack. So this is the vulnerability point. The reason we want to know about the VP, in short, vulnerability point, so is that we can now determine where we want to patch it. And it can be in the caller or the function itself. We will see soon. So this is a code analysis of a friend from the team. His name is Michael Hiley. And what we can see is the W char is Y char. It's the Unicode, and the ptoke doesn't get any arguments. And it's a class, of course, but by the name tokens. Again, the symbol from before. It's about the name. And we can see here the actual buffer that gets overflowed. So notice there is the n size and IDX input. We will talk about it later. Okay, so this is the C++ translation of the code, and what we can see here, if you have, okay, so we can see here actually that it's like str token of the C library, and the problem is that there is no check against the size of the destination buffer. So you can see that the end size here is the size of the input we supplied. Okay, so it doesn't really matter. It's copies until the end of your buffer, not the destination buffer. So what the ZERT patch actually does is a simple thing as this. To check the end size, this is, again, the input size of our string, and to return if it's too large or above 256 bytes. So I ask myself, why does Microsoft write this ptoke rather than using str token? Okay, so we can see that ptalk is C++ and it has its local storage, which is an improvement for the str token one, and it supports multiple concurrent reads if we think about threads and stuff like that. So str token can be used only once per thread, and in this case, it doesn't change the original string. That I'm not sure why they needed it, but this is the way it works. So if we actually give it a string in ZERT with Rust, for example, or do we, its result in the next strings returned every call is in ZERT with Rust. Every time we call this ptalk, this is what we get. So actually, if it was used by str tokenizer, then the input was nullified. So we have the in, and then it's a null character, and then ZERT again, a null again, and the input string is destroyed or touched. Maybe they didn't want it. Oh. So we talked about threads. So now that we know that the vulnerability point and the function that that allocates on the stack the buffer, and we want to patch it. So eventually we need a way to find where to patch the file, okay? Whether if it's in memory or if it's on disk, we need to patch it and find something that will tell us this is the place, this is where you have to change the code and fix it. So for example, we need a sequence of a few bytes, probably. It can be short, long, it doesn't really matter, but the point I'm trying to say is that if we use a mask like wildcards, if we have this GIF87A or GIF89, then it becomes GIF8 asterisk wildcard, whatever comes in, and A. So yes, it also can be GIF now 85 that doesn't, that is not wanted, but you get the point. So because there is a mask, we can miss the, actually no, again. We use the mask in order to find the same code in different DLLs. Because we said earlier that the code might change, or... Okay, so what I mean in genericness is a plus that the code changes among versions, and you want to track the same piece of code that you have to patch. So basically, if you can come up with the same mask or sequence of bytes that will locate the place you want to patch, then you're good. Otherwise, you will have the need for a few more signatures for the same patch. Okay. So we said earlier, and we showed the code, the translation in C++, that the ptalk is a small function, and it's only used in one place. So there is only one caller, and the function is so, I don't know how to say it. It's not used widely, so nobody cares about it there, and we can easily find it. So this goal here is to use the whole function as a signature, and the reason for it is because later on, if Microsoft themselves patch the file, and the new function will get changed, and the old signature that finds the patched code won't work anymore because it's now patched and it's for good. So what I'm showing here is the xdump of the function we saw earlier, the ptalk function, and you can see this two blue bytes here, and actually what I did is like string comparison, but I wanted to show it visually to you that if you take all the versions of the DLL and come up with the xdump, there are only two versions that collide. So if you take, say for example, the first version and the second, and put them one on the other, this is what you get, and this is where we see there is a problem. It's not the same code all along the versions. So we need to see how we bypass this difference. So the reason for this change in the 2 bytes is this. I took the disassembler and I disassembled the following instruction that if we get back, you can see that the whole instruction begins before the blue bytes. So this is what I did here. Okay. So this is the 2 versions. They're actually the same instruction. It doesn't really matter if the I word of the EDX gets zeroed, but the result is the same. So we know it's the same code. I really don't know why it's happened. So that's why I said compiler's bad day. And it doesn't really matter for us. We only have to match the same code. So eventually we have to patch the vulnerable code. And this is what we do. If we look at the code, we only have to add these 2 instructions, the comparison with the length of the input string. This is the end size. And again, we use ECX because it's point to this, the instance of the class. And if it's too big, we return null. So there is only one problem now that we still have to solve, and that's the Windows file protection. So the Windows file protection is actually good for the end users and bad for people like us that want to change the system files. So what I did is examining the export table of the executable. We know it as VGX DLL, and I saw these exports. DLL can unload now, DLL get class object, register, unregister. So if you're a bit familiar with COM, you would notice this is the interface for export table for a COM DLL. And now that we know that it's an in-process COM DLL, we can easily register and unregister it. And this way, we actually indirectly bypass WFP. Or to be honest, WFP doesn't even affect us because we can redirect the path of the COM DLL file to our new patched file. So this leads to the next thing. That means that we use an on-disk patching in this case. And again, antivirus issues. Actually, one of our team members named Nick Fitzgerald, a Lajon from the antivirus industry, took the patch I wrote and stuck it somewhere in, for example, virustotal.com, but something much better and internal for his use, and came up with the list of all antivirus and how our patch affects it. So luckily, nothing was wrong, and because actually, if you think about it, a patch it takes an executable file and changes it, and it's like a virus. But we have a good purpose, unlike a virus that wants to damage your computer or whatever. So antivirus issues was not a problem eventually, and another thing to say about it is that now you can write a COM virus, and no antivirus in the industry will find your file. So you can patch the file, and your code will run, and the antivirus is useless. So again, about the ZERT patcher, we will see the few steps we do, and the key thing here is to write the patch as simple as possible. So you can see the steps and read the file, search for the binary signature, and then just replace with. We saw that we have all the signature of the whole function, and then we have to replace the file with the corrected code. And we'll see it later. And save the data to a new file, and then unregister the original file and register our new file. And this is, again, the indirectly bypassing the WFP. And our patcher also supports GUI and console for administrators to deploy it in their own networks. So now I'm going to talk about, okay, so again, Microsoft can simply look at their code, see the vulnerability, and recompile the source code with their own C or C++ patch. And for us, it's a big headache. We have to make room for the input size test. We added a few instructions there for the comparison instruction and the branch. And now we have to take the code and make room inside of it and put the size validation. And yet, we want to preserve the functionality of the PTOK, the parser tokenizer. So the first patch, what we did was MS patch only copied the bytes until it reached some point. It's the end of the buffer minus white char null character. And our version 1 patch says only don't copy the buffer if it's too long. Don't be permissive and give it the chance to get to the end. Just if it's too long, there is a reason, and probably it's the 0 day. So what we do is later on we change it, and this is the patch version 2 that Microsoft already released their official patch, and I took the coder and crunched it. It means to preserve the functionality of their original code and with their own size validation and make it from 6.3x to, again, 5b. And this patch is exactly like theirs, and there is another plus that, for example, okay, I will get to it later, but in few words, that, for example, Windows 88 is not supported anymore, so this patch still will work for all the platforms. So there was another problem, and this is the 64-bit patching. And actually, we don't know of anyone who used it, but it's really interesting, and it was fun and challenging for me to do it. So at the time, I didn't have a 64-bit CPU, so I couldn't run Windows 64 bits and just like attach a debugger to Internet Explorer and try to see where the overflow happens, and then immediately find the vulnerability point and patch it. So what I had to do, and I will get to it shortly, how I found without a debugger and Windows and dynamic debugging the PTOK function. So there is another thing with a new cool feature in 64-bit CPUs that you have the RIP, that's the IP, the current instruction address, and there is a RIP relative. You can actually load data from some offset that is relative to the current offset of the executed code. The reason it's problematic is that if I have to patch the file again, then I have to take care about the RIP relatives instructions, because if the original offset was +5, for example, and then I get the instruction a bit down, then it has to be, for example, +3, and it's really important. Another thing is that soon enough I'm going to show you that Microsoft actually changed the code in the 64 bits, and yet the 32 bits version is unpatched. So this is the assembly listing of the 32 bits and the 64 bits. So here we can see the call to PTOK. This is the caller. This is where the actual stack gets overflowed, and this is the assembly listing of the 64 bits of the same place of the instruction, and this is the vulnerable function. So basically, you can see the right side is showing the loop of the memcopy, but the special one, like the PTOK, and this is the calls to PTOKs. And in 32 bits, it was called twice, and now we can see that it's only appears one as an inline function in the 64 bits. This is something that the compiler won't do on its own. It means someone changed the code, and yet the code is still unpatched in 32 bits back then. So I had to find a way to statically find the PTOC in 64 bits. So what I did after thinking a long while was to use this immediate here, which is a return code to some, we can see that it's moved to some EAX pointer, but it doesn't really matter now. But what I'm talking about is this. We can see the same immediate value in the 64 bits and in the 32 bits. So all I did is searching this double word or 4 bytes in the 64 bits version, and it only appeared a few times, if not once. I don't really recall now, but it doesn't matter. It's really easy to see it's the same code after all. So this is the VML patch, and I will continue now with the animated cursor patching. Okay, so, okay. The Windows animated cursor is already patched by Microsoft, and in 2005, someone from EI found a vulnerability in the user32 DLL about the animated cursor files. So actually it was fixed by an MS update, security update, back then in 2005, and XP is already immune, but it wasn't fixed well, so that's why there is the incompletely, because later on in 2006, a similar vulnerability in the same area of the handling of the ANI files was found by Alexander Sotirov. By the way, I talked with Alexander in Black Hat, and he doesn't know how it's got to be a 0-day in the wild. Maybe someone leaked it from Microsoft or in the chain between the companies. It's not clear. Anyways, the bug description. So there is this RIF format. It's really popular for WAV files. I'm sure all of you know it. And the thing is that it works with chunks. Every chunk has its header name, and the data following it. So now I'm not going to talk about the way I reverse engineered the vulnerability point and how I found it, because I didn't do any of it. It was another member from the group that released a paper about the patch 2 days before I actually started to work on this patch. So I used his work, and that's again the member I talked about earlier, Michael Haley. So this time there is this load cursor icon from file map. So it loads and passes the file from the memory. File map is the file in the memory, and this is for performance issues probably, to load the whole file onto the memory, and then you can read it faster. So there is a chunk named ANI-age. It's the ANI header, and it tells its loader or player how many icons there are inside the animated cursor. And this one is passed later by load ANI icon. So after we pass the ANI header, there is another parser for the chunks of the icons themselves. And this one is done by load ANI icon. So what we can see here is the malformed animated cursor file, and this is actually the ASCII dump of it, and it was enough for the thing I want to show you. So we can see the RIF and the icon, and then the first ANI header, okay? Which is correct and in place, and comes here to talk about the next icons it's described. So the first header chunk, and so far so good, everything is fine. The patch was already fixed in 2005, and now you can see. Okay, so this is the trick. The ANI header chunk is here again, and this time it's passed by the load ANI function that it was supposed to only pass the rest of the icons, and for some reason it passes again the any header. And maybe it's a problem in the design of the format of animated cursors. I'm not sure. But anyways, it did the job well. So the attack vectors, actually Internet Explorer can load the file really easily with style cursor, URL, malformed any, and you don't have to do anything else. And of course, Outlook and Outlook is vulnerable too because it can run HTML, because it passes HTML, and Windows Explorer, the shell itself, because if you have an .ico file in the folder, shell will show you the thumbnail of this icon and pass the file, and the code will get executed. So about the patcher. So this time we have to patch user32 DLL, and this DLL can be found in all processes, of course, at least the GUI ones. And therefore it requires a memory patching. So instead of going against the Windows file protection, all I had to do is use the known DLLs. This key in the registry tells the loader to load our DLL file that will patch the file every time again, and in every process. So basically, if Internet Explorer is ran after we change the known DLL's key in the registry, our DLL will run and do its stuff. So the stuff is magic work that we will soon see what's going on. So this is the load any icon, and this is where you can see the switch, or in assembly, the switch case in C. And this is how it's translated to assembly, and you can see the compare EAX with sequence, list, rate, and the any header again. So we said earlier that it was passed in the color of the load any icon, and now it's passed again, and later on what really does the overflow is the call read chunk. So we know that we have to patch this function. And this is the XDump of the same code, but I wanted to show you the D-words and the signatures I'm going to look for. So there is the list and the any header. So basically I want to find the switch, the cases of the switch. And if you wonder why this time it's list, and you can read it, and here it's TSIL, it's because the indianity and how it's laid in memory. Okay, so this patch is actually a new technique, and it's about generic patching, and unlikely the earlier patch of VML with the mask, this is a much more, it's a better patch. Let's see why. So we have the read chunk, which actually mem copies the buffer, and it needs a fix. The problem is that there are 3 cross-references, 3 callers to this function, and we only want to patch the one that actually triggers the exploitation. Because, again, we don't want to change match the file as less as possible, touching it and to not break its functionality. So what we do is searching for a static signature, and this is what I say, like a look back to find a signature, and then disassemble forward until the next call is found. I will show it again. So what we want to find is this D-word, the any header, the list, and then we know this is the area in the user32 DLL that we want to find. And if we keep on disassembling, after the any header, we will reach to this call that we want to patch. So that's why we need a disassembler here. Okay, so now we found the indirectly call to memcopy, because the read chunk itself calls another function that does the memcopy, and it complicates the stuff a bit, and we'll see why. So the fix. So I took the read chunk function and rewrote it with the added validation. And this time I didn't have to crunch the code. I have all the room I needed. And again, it's pre-compiled. So I just needed an assembler and took the code and added the test and recompiled. And there is only one problem now that I talked earlier. The mem copy is the read file PTR copy. So our read chunk, because the nature of the 32-bit and or even in x86, that calls are relative to the current position they are executed. So we have to like relocate the address of the call from the read chunk or the new read chunk, because it's now patched, to read file PTR copy. And therefore it means we have to find the read file PTR copy, the address of it, and relocate our new function. So what we do is a fix for the precompiled call, and again, calculate the relative 32-bit offset of the file. So what we have to do, if we talk about technically about the API to use, you can't use, for example, malloc because, or memory alloc, however you will want to call it, is because it's in the heap, and the heap is not supposed to be executed, and therefore what we have to do is to use, for example, virtual alloc and supply the flags for telling it is an executable code. So after we did all these things, and this is part of it is in precompiled and part of it in runtime, we have to relocate the original vulnerable code. So the read chunk has to be patched to the new allocated function. So some problems we might encounter. If there are multiple threads, might run the patched code. So if you patch a sequence of bytes while a code is running in, the same code is running from a few threads, you might screw up some of the threads because the code is not synchronized and it might run some garbage code. So that's why we patch only a D word, and that's the offset we relocate to the allocated place. And there is no problem with it because we can do it atomically. And another thing, that when we search for the signature, the any header and the list, we have to search for a D word, but it must be in a byte aligned, because if you make a C for loop to look for if you scan the list as a long pointer, it will find it in jumps of a D word, and then you might miss the D word you really want to find because it can be misaligned. So we look for a D word in byte aligned. This is tricky and crucial. And again, to find the call to the read chunk, we have to use the disassembler. Because, for example, if we want to find the E8, that's the byte that means it's a call instruction, and it can appear as a part of another instruction. And then if we run on the code and find the E8, it might be something else, and we can screw up the code and the patch won't work. Therefore, we use a disassembler that will disassemble the stream, and we then get the accurate instruction and its address. And there is another problem with if-then statements, because the way they are generated, it might branch to, for example, there was the comparison with the any header. So if there is a branch, okay, compare EAX with the any header D word, and then there is a JZ. It means take the jump if the value is found, and then you have to follow that branch, because if it generates Z, you have to run with the flow. So you have to be code flow aware and notice this little stuff because it's important. Otherwise, you can miss the real call you want to follow. So that was it about the honey patch, and maybe I'm not sure I really explained it well. You will have some time to ask questions. So I wanted to talk about the sad truth about these patches. So again, about the animated cursor, after the buffer was mem copied to the stack and it made the overflow, it only then, the code only then assured the file. It's verified the size of the buffer only after it overflowed the function. So this is a bit ironic thing. So another thing is the VML. The VML vulnerability didn't exist back in Internet Explorer 7, but only some versions of it, and of course now it's all already patched. But I ask myself if it's not patched back then when the 0 day is, if it's already patched back then when the 0 day was released or in the wild, then why Microsoft didn't patch the Internet Explorer 6 in time or before the 0 day? So they knew there is a bug and they didn't patch Internet Explorer 6. This is pretty annoying, but maybe because they have lots of source code and other teams that work on Internet Explorer 6 and 7 and they don't cooperate well. I can't answer really for that. Another thing is that, and notice this, Internet Explorer 5 had the validation test for the VML. So if you had basically Internet Explorer 5 today that you wouldn't do it for any sane reason, then you would be protected. So eventually, ZERT is just another third party and that supplies patches. So I'm going to say it simple as that. Do not use third-party patches. Yes, Gil Dabach said it now after all his hard work and for a reason, but let's see why. So do you really trust the people that don't have the code or didn't write the code themselves? I mean, you have the source code, or actually only Microsoft has the source code, but notice the emphasized word source. It means we have the code. We can disassemble or reverse engineer the code, but the source code is maybe what matters. But maybe not, because after all we did a patch. So, but again, about the third-party teams or companies, whatever, who supplies the patch, can you really trust them? And how do you know they know what to do with the patch and what can be there? And so there is another thing about liability and vendor support. If ZERT now is gone, or even if it still exists, you can't come and say, hey ZERT, I used your patch and now Internet Explorer or Windows doesn't work well. There's nobody to talk to and it is released under the GPL as far as I know now. Maybe we will change it to another license later, but the point is that if you have Microsoft behind the patch, you can seriously trust it and know that they will support you. But yet again, for Windows 98 or Windows 2000, they are not supported anymore, and someone has to help them if people still use it, and people use it. So again, do not use third patches, but, and there is always a but, there is a risk management you have to do. Okay, so why not to use third patches on the other end? Because if you're already vulnerable, then what can be so wrong? You can just maybe get protected or maybe get owned by some hackers team that pretend to do a patch. But that's why some of our members are really popular and are known widely, and they are security experts. So, and another reason is, do you really want to stay unprotected? I mean, vendors today like Microsoft or other companies take their time and they have to do lots of QA and test, and the advantage here that we can do it rapidly and make sure it works for at least some of us, but nobody is perfect, and we'll see it later soon. And we supply the code. You can review it, do anything you want with it, patch it again, add your own stuff. Although I guess it's pretty advanced, but After all, a patch is just another piece of software. We can see it with EI's patch that was bypassed, and if you go to Mealworm, you can see that it was already bypassed, and actually EI admitted it was patched. So now you have to patch the patch again, and it doesn't work like that. So far, ZERT is good, and our patches work well. Okay, so this is a small demo I made. And again, I used Mealworm's code. So it's supposed to open calc. It worked. We're here. Now, if we see the fix batch is registers the, you can see the VGX DLL and the vulnerable VGX. It's an old DLL I brought with me to show you that now that the VGX is, and this is the patched by Microsoft one, is registered, and then I will, Firefox, just a moment. Well, with Firefox, nothing will happen, so, but let's see Internet Explorer. So now you are protected and the exploit won't be triggered at all. You see, nothing happened, and if we take a look at the code, this is actually the fill buffer with the string, the overflowed one. This computer is slow, just a moment. Yeah, it's ipspray, and it's not my code. I took it from Mealworm, and the credit is. Okay, not bad. Oh, all right. So you can see it metasploits Skyline and invokes the calc. But what I want to show you that this is the fill method, and with ipspray attack, it points to the ip. So if you have dep, you are good to go, and it won't work. But there are other ways to exploit this. If they know in advance your version of Windows, and they can bypass dep. So, questions, tomatoes, anyone, I guess? Anyone here? Everything is clear, because I'm sure there are lots of technical stuff here, and oh well, I'm done. Thank you very much.